Okay, hello everyone. So for today, I will be presenting this paper by the title 3D face model reconstruction from a single image, the feature aggregation approach using a hierarchical transformer with weak supervision, which is published in 2022 in the ACM Neural Networks journal. Awesome. Okay. Okay, so let's see what is the main contribution of this paper. So for this paper, they are trying to use the feature aggregation method, which is the hierarchical transformer that is used to aggregate a single image features of the 3D face constructions, which is capitalizing on the handling of spatial relationship. I will explain this method in detail later. They also used some weak supervision technique, which is in order to reconstruct the 3D face, since they don't have the label 3D data set, they have to use a weak supervision technique in order to render the 3D face. So finally, they use evaluation and benchmark. They conduct a very intense comparison with the current technique, which shows the proposal method effectiveness and efficiency in the 3D face constructions. So just to give a little bit of background, in the face reconstruction, most of the techniques is done by using the 3D face model. So in the 3D face model, there is a 3D face with a certain number of end vertices and face textures. So the 3D model can be modeled by using this expression, which is S, and T expression, which is texture. So on the shape expressions, on the shape module, we have the mean shape, and also we have identity and expressions. So this identity and expressions are used to regress the shape of the face. And the alpha, like this identity and expression, is regressed from the given image and given to the 3D model to reconstruct the face. So as you can see here on the right, on the given an image, we use some kind of CNN model to regress identity, expression, and pose. So this identity and expressions will be used to reconstruct the shape. The CNN also outputs some kind of textures, which means the basic skin tone and intrinsic attributes of the face in order to reconstruct any kind of human faces. So for this particular paper, they are trying to achieve, like using CNN have its own limitation. So they try to remedy this limitation by using transformer as a backbone to regress this expression that could be used to reconstruct the 3D face. So this is the overall structure they have. So the main idea to keep in mind here is the idea of this model proposal is to regress this number of parameters, which is identity, expression, pose, and also different number of lightning and other parameters that can be used for regression. So they start by given image. They divided the given image into patches, and using linear embedding, they use a swing transformer block, which I will explain better, and they use the output of this first stage into the second stage, and the second stage will be used in the third stage, and the third stage will give the fourth stage, and which is the high resolution output of the given image. And they try to aggregate the features that is getting from intermediate result of stage 1, stage 2 to stage 4, and using feature aggregation module, they try to concatenate it and use it to regress the coefficient that is needed for 3D face constructions. So we'll come back to this in detail. So first, let's see how they use the swing transformer module. So swing transformer module, like they try to adapt the swing transformer module for efficient extraction. This is because the traditional transformer module, it does have some global attention, and global attention have its own limitation, specifically when we try to process the image. And instead of using the global attention, they use window-based multi-self-attention and shifted window-based multi-single attention. So first they tokenize and they do embeddings. They process inputs into the 3D tokens, partitioned into non-overlapping windows for self-attention, with focus on dimensionality and efficiency embedding. So the reason is, in order to calculate the embeddings, they try to divide the image into like 4x4 patches. And using each patches, they try to calculate the window-based self-attention. Like this block only calculates a single patch within its own location. And this shifted window just calculate some shifted calculation of each window, which is related to the given image. So first, like they have this window multi-self-attention, which is proposed by LN, which is like layer normalization, and they give it to MLP. And after that, the MLP output will be used in shifted window multi-single attention. Then finally, they give it into the MLP. In order to see how the model works, let's see the 3 components of this model. First, the 4-stage feature extraction. So extract features at 4 scales. As you can see here, in each stage, we have feature 4, feature 3, and feature 2, and feature 1. So each stage will output some features, and these features will be used later to aggregate the final output. So embedding and tokenization, they try to divide the image into patches, embedding them into higher dimension for efficient processing. So first, the given image, they try to divide it into 4 patches, and this is just the dimension of the patches after they divide it into 4. And after that, they give it to the stage 1. The stage 1 use some linear embeddings and the swing transformer, and it will output some features that contains a certain number of vertices and dimension. And on the second stage, they also try to divide it into 8, and they increase the number of channels. And on each stage, they just increase the number of channels, and they divided the image into multiple patches. So the idea is, on this stage, stage 1, this swing transformer will capture the low resolution and high features relationship between the image. And the final stage, in theory, will have to capture the high resolution but low feature relationship of the image. So by concatenating the intermediate result of this 4 output, they try to regress a high quality coefficient that would be used for reconstruction. So the model uses multi-scale feature aggregation. This multi-aggregation module, which is FAM, it is used to merge high and low resolution feature maps, addressing a semantic gap between different resolutions. So as you can see here, the gap between stage 1 and stage 2 will be remedied by the FAM, because on the stage 1, we only have a high resolution, and on stage 4, we have a low resolution, and we need to have some kind of module in order to aggregate the 2 gap between those features. So the detail in the high resolution features utilize bilinear upsampling and convolution to align spatial dimension and channel depths, enhancing the detail, salience, and the feature utilization. So when we try to aggregate the output from the stage 1 and the stage 4, they have like spatial, the spatial dimension is not equal. So what they do is, in order to match the spatial dimension, which is output from stage 1 to stage 4, they use somehow bilinear upsampling. The reason they use bilinear is they're trying to upsample in 2 dimension. As we discussed yesterday, bilinear is just trying to interpolate the new points by using 2 existing points, and they try to do that when they reach 4n in 2D, which is 4n is the input token, and these the input dimensions. So in order to concatenate with this input, which is the desired dimension, they have to upsample n 2D, and they have to concatenate it together, and finally they have 4n 2D, which is n is the multiplication of the height and the width of the image. So the training pipeline is as follows. This paper used dual training approach, which means they use both unlabeled and labeled face image. The reason is, like, since some of the method use the 3D WMP dataset, which have like a 3D parameters for supervision learning, and also use like parameters regression image synthesis. The regression network enhanced with the feature aggregation, regress key features, which is then used to render the generate and composite the final image, which means in order to reconstruct the face, since they don't have all the 3D label dataset, they have to use some rendering technique to compare with the render input image and the input image they have from the dataset. So loss function is defined as follows. The loss function, first of all, they use different kinds of hybrid loss function, which compose landmark, which compose also photo loss, perceptual loss, shape loss, and finally they also employ adversarial loss. Let's look into each of them. So first, landmark loss. This is the usual loss when it comes to facial reconstruction, which means they try to compare the landmark loss between the reconstructed image and the input image. So the QN is the 68 landmark on the reconstructed image, and Q prime is the landmark on the input image. So they just calculate the little difference, and this is the landmark loss they use. So the second one is the photometric loss. It compares the rendered and actual image pixel by pixel, and this also can be adjusted for occlusion to enhance some kind of realism. So I prime is the reconstructed pixel image, and I is the input image. So they just do some L2 difference to calculate those. Also, we have perceptual loss. Perceptual loss is they use some deep feature pre-trained network, which is VGG8 pre-trained deep feature extractor. So what they do is they try to extract the deep feature between the input image and the reconstructed I prime image, and they calculate the difference based on that. The shape loss is the direct comparison between the predicted and the actual 3D shape. This is used for refining facial accuracy, and S prime is the reconstructed face mesh, and S is the 3D ground truth mesh they have from this particular data set. Finally, they use adversarial loss. For adversarial loss, they use the min and max optimization. So DS prime is the adversarial loss for S prime, which is the reconstructed image, and DS is the adversarial loss of the input image. So basically, this is the loss function. Given the ground truth face image, they use the Sween transformer block to regress the identity, expression, texture, and the pose of the image, and also the lightning in order to reconstruct in order to render the input image. So lightning is very important in order to render the face, any given face image. So they use differential rendering to render the face, and to calculate the loss. They just use landmark detector to detect like 68 key points on the face, and they use those landmark detected key points to calculate the landmark loss. And ArcFace is the deep feature extractor, which is based on VGG 19 architecture, and they use that to get the deep feature of the input and the reconstructed image. So for this particular shape loss and adversarial loss, they used 300W LP. So this dataset have its own ground truth shape and its own ground truth texture parameters as well. But the thing is, this 300W LP doesn't have high resolution. For example, for the shape, what we are looking for is like 35,000 vertices, but for this particular data set, they only have about 100 vertices for the shape, which is not high resolutions. And for the texture, for like, in order to get a very detailed texture, we might need about like 35,000 number of vertices by color RGB channels. But for this one, they only provided, if I'm not mistaken, and about 115 texture vertices with along their channel, which is a low resolution texture to say the least. So this is not very attractive way of calculating loss, but it might help to somehow to reconstruct the shape loss when there is a huge occlusion, and that kind of state can be easily remedied by using this 300 WLP dataset ground truth shape. And based on that, they try to calculate, they try to give it to the back propagation for this swing transformer block. So the implementation, they use like a SLAB-A dataset, which is the de facto dataset when it comes to face reconstruction. It contains different kinds of pose and different kinds of occlusions and different kinds of identity, which makes it ideal for face reconstruction. They also use VGG phase 2 dataset to train for weekly supervision training. And they also use like 300 WP for supervised training as well. So the training approach, it uses like two-step training process with unsupervised training on the split of SLAB-A VGG2 dataset. And they also follow the labeled 300 WLP data to calculate the shape and the adversarial loss as well. The loss function, I already talked about it. They employ landmark photometric perceptual loss for initial training, and they added shape and adversarial that is getting from the 300 WLP dataset. For implementation specification, they experiment with different swing transformer modules by varying the number of head and the number of layer on the swing transformer, and they experimented with different parameters as well. So this is the qualitative result they have. This is the ground truth image, and they try to reconstruct the face with their own model. This is their model. As you can see here, the texture is not as accurate as the ground truth, but we can say it's high resolutions, and we can see the basic skin tone, and we can see also the basic intrinsic attributes of the face after the reconstruction, you can say. This is also some qualitative comparison with the shape and texture occluded image as the ground truth. So one of the benefits of this paper is when it comes to occluded image, this paper does pretty well because of the shape and the adversarial loss they use from 300 WLP dataset. As you can see here from the ground truth, this person have some kind of beard. Let's say this is like considered as occlusion when we reconstruct the face. But as you can see here from their model reconstruction, their realism is pretty good, and it can generalize very well. A person have different kinds of occlusion, sunglass and hats and everything that happen when the face is occluded. So this is qualitative results they have. They use like a mic dataset as a benchmark that is facilitates the comparison for the face shape. So they use like face reconstruction error. This is their model. As you can see here, their model outperforms some of the very competitive state-of-art work which is proposed before this paper. And this is their experimentation with different kinds of Swing transformer. So this is the Swing Tiny, which is trained on 100K by using different parameters. This is a different dataset, which is the dataset which is indoor, outdoor, and they also calculate the difference between fusions, and they use like this is the base model, this is large, this is small. So they try to calculate like they try to determine which baseline or which network outperforms the rest of the variation of the Swing transformer model. So one of their qualitative result is focus on they try to study what's the benefit of using different kinds of backbone for 3D MIM purpose. So this is the backbone variation they have. So using Resonate 101, using efficient NATE, using Swing baseline, and using Swing baseline with FM, which is the feature aggregation module. Using Swing base model plus the feature aggregation module, as you can see here, outperforms most of the metrics they have, which is for indoor and outdoor. So basically, they conclude that this feature aggregation module helped to generalize the model very well because it concatenates the high and the low features together and outperform the state-of-art works. In conclusion, this paper proposed the hierarchical transformer architecture. In each hierarchy, the model outputs some intermediate features, and those features will be aggregated finally using the FM, which is the feature aggregation module, to finally output a good result. And they also use hybrid loss function and semi-supervision training. This is a very common way of training when it comes to the 3D face construction and alignment. And finally, the performance and the realism is much better because of the 3D WLP dataset they have in order to remedy occlusions and enhance realism. So this is the presentation I have for today. If you have any question. Should I still stop? Yes.